Hey, so hi everybody. Yeah, we're gonna do an intro to Rust, which is this like cool new language we wanted to talk about. I guess before we start, just really brief personal information about me, so you know where I'm coming from. I most recently I'm just kind of an immigrant from tech law and policy. So I did my law degree and PhD in the kind of network neutrality area and vertical integration, that sort of thing. But before that, I kind of ran the tech side, network side of an ISP for a number of years, and been writing software forever. And it's just Rust is kind of a really interesting new technology that really caught my eye, and I thought I'd kind of share with I guess local people who are interested in it. So. I'm not necessarily a super expert in Rust. Like I'm not part of the team developing the language itself, but I've been working with it for a little while. So I guess think of me as like a tour guide, and I'll even I get some pointers to some of the official resources, but I can kind of give like an overview, some of the details. So anyway. So it's just Rust's unofficial mascot, kind of like a play on words. Like some Rust people call themselves Rustaceans. So the mascot is a crustacean. Yes, lol, kind of a pun. Anyway, so Rust is pretty new. You can see it's on the TIOBE index for like how popular the language is. It's still less than 1% of people who are actually using Rust and actually writing Rust code. But it's been really popular for reasons that I hope are somewhat obvious after we go through the talk today, and has been getting a lot of like attention and interest from people, even if they can't like start writing with it now, or the projects aren't appropriate. It's really kind of interesting because it's doing something new and valuable that there's not really a good analog. There's not really another language out there that does what Rust does right now, at least not one that a fair number of people are actually writing code in. So this is, just one way of categorizing programming languages between system languages, so-called systems programming languages that have, really high performance and a lot of low-level control on one side. And on the other side of the spectrum, you have these kind of high-level and scripting languages like Python and JavaScript. And then the sort of middle category where you have, things that are statically typed, you've got garbage compilation, or garbage collection, you have, it's got to be compiled ahead of time. Maybe it's to native code, maybe it's to some intermediate format that's JITted, but for the most part, there's this kind of sophisticated backend virtual machine that takes care of a lot of the memory management. So you don't have to worry about kind of all of those low-level details that you would have to worry about if you were writing, in C or C++. So the reason that Rust is really interesting is because it shakes up this picture a bit. It's more targeted at the niche that's currently occupied by C and C++ in that it's designed to be usable for systems programming. So you can do things at a really low level. There's no runtime, there's no garbage collection. You don't even need an operating system. You can write to bare metal if you want, or you can use it to write an OS kernel. It doesn't need any of that like runtime support that you'd need from like C# or Java or Go. But at the same time, it still provides memory safety, which before now you really wouldn't have had in C and C++. And that's really one of the major, the real major kind of value proposition of Rust is that you get this, very high performance and low level control. But for the most part, with the exception of, this sort of safety valve for unsafe to like build abstractions and that sort of thing, most Rust code is actually memory safe. And, that's a pretty big deal when, you need to write code that's reliable, and especially code that's network facing, where, like a memory safety problem could turn into remote code execution. And suddenly now you've just, adversely affected, everybody who's using your software. So, Rust isn't appropriate for every application, but if you've got to have both this low-level control and speed, and you also would like to have memory safety, kind of Rust is the way to have your cake and eat it too, a little bit. So unsurprisingly, having your cake and eating it too is actually pretty popular. And as a result, Rust has been at the top of Stack Overflow's list of most loved programming languages, actually every single year since 2016. And as you can see from the chart that I put in the presentation, it's not by a small margin either. That's a pretty sizable lead. Now, Rust kind of has an advantage in this because it's a relatively new language that's targeted at a specific demographic and a specific set of applications. So, the first people that are going to use it are going to be the people who for whom it has the best, potential value, right? You're not going to use something unless you think it's actually better than what you're currently doing. But I think something you kind of can take from this is that Rust does make some kind of big promises in terms of having both things that are normally you have to trade off, and it's kind of coming through on those promises. So this metric is actually, if you read it up in the corner, that's the percentage of developers that are currently developing with that language who want to keep doing it. So it's only of the universe of people who are already writing Rust, more just think it's really great and want to keep doing it. So that's a pretty sweeping endorsement. And this is kind of interesting. We were talking before before things started that between the time that we had originally scheduled this talk and today, there have been this is like a thread on the Linux kernel mailing list where they're actually talking about having some Rust code in the Linux kernel, which is really interesting. I assume for drivers and that sort of stuff initially, but maybe for other things in the future. And this is kind of interesting because Linus was pretty famous for not wanting to accept any C++ even, and to have them consider supporting Rust actually in the kernel tree is, I guess, a pretty big step. So it's interesting. I guess we'll see where that goes. The biggest concerns I guess they had in this thread were will there be kernel bugs? Will get enough testing, that sort of stuff. So it wasn't like an outright rejection of why would you ever want to do this, which is always a risk when you're proposing something new especially in the kernel. So anyway. So I said that, I was kind of like a tour guide, not one of the experts in writing the language. This guy actually is. His name is Steve Klobnik. I'm sure I'm pronouncing his name wrong somehow. Is one of the authors of the Rust programming language book and is on the core team. So there's an entire kind of really interesting presentation about how Rust handles these kind of trade-offs and sort of looks for new approaches to get to some sort of win-win. And the short answer is, kind of summary is that, there really is no such thing as a free lunch, but sometimes there's a compromise in some other direction that you can make. So this is, I guess, I have a little clip from him. This is actually from a different presentation, but just to kind of break up the monotony of me talking through a PowerPoint the whole time, I thought I'd just give him a minute of kind of explaining their approach to the trade-offs. So hopefully this works for
in this
everybody.
talk. But like we sort of had this dichotomy where it's like, yeah, you can either use a language that's nice to use and easy, but also extremely inefficient, or you can use something that's very, very fast and very, very dangerous. And so like Rust came along and said, why can't we actually have both? And the answer is because everything is always a trade-off. So Rust is like, haha, we have speed and safety. But the thing is that you're always paying somehow. And so the answer in Rust case is it's more difficult to learn. And there's a lot of like slower compilation. You get a lot of compiler errors because the compiler is very strict. And so it takes a little more time to get going with Rust than it does with something like JavaScript. So there's always a trade-off somewhere. Whenever somebody has a slide and they're like, look at these two bad things, but I have something that's better than both of them. Like, if they don't tell you why that's also bad, they're just lying to you, probably by omission. And so this is actually...
Yeah, so was everybody able to hear that? Did that come through okay?
Yeah,
cool.
It came through.
Cool, because I got, I think, one or two more clips later on that are kind of fun to hear, like war stories from people that actually went through some of the stuff themselves. But the whole what is the kind of having your cake and eating it true is like they want to avoid some of the the traditional problems that you have with manual memory management, things like freeing something twice, or using a variable after free, or dereferencing a null pointer. And then Rust actually has, in the type system, kind of prevents certain types of data races too, which is really useful for parallel programming, and we'll get into that a little bit later. But actually, and this is Nico Matsakis, another member of the core team, and we'll hear from him again later in a couple slides. But when you have to make these trade-offs, you're always making some sort of choice between them, and so exactly what you do is going to be informed by your kind of values and goals for what the language is. So Rust sees its values as primarily this memory safety thing first. Because if you don't have security, what do you have? It's just kind of it's a non-negotiable thing to have memory safety and reliability and security in kind of modern applications, especially the sort of systems that are going to be interacting with the internet a lot, right? Because you're constantly living on an attack surface. And then the next is speed, because people aren't going to adopt a language for these sorts of things unless it's reasonably performant. And then developer productivity, because obviously you have to get stuff done in the real world. If it's absolutely impossible to do something in, it's just not going to get used. It's just going to be an academic curiosity. So, they do kind of focus on that also. But the whole memory safety thing is a pretty important thing to a lot of people. The C and C++ programs are really fast, but they're also kind of dangerous, right? Because you can pretty easily write bugs that have memory safety issues, and then it's possible, if people figure these out, it's possible that this could get turned into like a remote code execution. And so Microsoft and some other people have looked at this issue and kind of, they write enough software that they want to do a study of where most of their security bugs come from. And they found that, I guess you can probably see it in the headline, like, well over half, 70% of all of their security bugs were memory safety issues. So, if there's a way to structure the language in such a way that it's just no longer possible to express those memory safety type bugs in a way that the compiler will actually compile. So if like the compiler will detect them and not let you compile that code, suddenly if you could just not have 70% of your security vulnerabilities, that'd be a really huge win for everybody. So, that's one of the reasons there's just tons of interest in that. Um, I got, kind of one of the most infamous examples, the Heartbleed vulnerability was, it was a memory safety issue where there was just a bounds check was missing off of the heartbeat functionality in SSL. And if the client sent data in a particular way, the server would just send back a random 64K of memory that wasn't bounds checked. And inside that 64K was passwords and encryption keys and, other sorts of things that you'd expect to see inside of the OpenSSL memory space. So, obviously it's possible to write correct C and C++, but and I'm sure there are people who can do it, but not everybody can do it, and there's inexperience. There's also like coordination across time and people in organizations. Like, I wrote this okay, but why did this other person screw it up? But maybe the other person that screwed it up is you several months ago or even yesterday, sometimes. So to have the language kind of be the inherent safety mechanism there can be really helpful. And then there's also sort of this interaction between, that danger of writing things that are unsafe and will, basically make your program unsound and ready to crash. And then also developer productivity. Because if you have to constantly like be worried about that sort of stuff, like all the time and paranoid and figuring that out all on your own, that's going to like sap your a lot of mental bandwidth and energy for being productive in that language in the first place. So, it's sort of, little bit of two sides of the same coin there. If you improve the one in kind of a sense, you automatically improve the other a little bit as well. And, it's one of the big advantages of developing a language like Java or C#, is you don't have those same sort of memory safety errors. And so, it can be a big advantage. So anyway, this is the first slide with actual code in it, and I thought it would just be interesting to actually go through an example of just how easy it is to shoot yourself in the foot while using C and C++. So if you walk through the code here, okay, so walk through the main function. We're creating a vector. We're putting a bunch of items into it, and then we are taking a pointer to one of those elements. And then, after we have that pointer, we add some more elements to that array or to that vector. But because that vector had, let me see if I can use a laser pointer. Because that vector was only of size 5 initially, as soon as we add the 6th element, this is going to need to be reallocated in memory, right? You have to reallocate that and copy it over to the new memory allocation, and all of your old pointers are going to be invalidated. But we had saved one right here. So in the rest of this code, you can see this, there's cout, the value is at this pointer, and so here's that address. It's at this hex address. That's where the third element in that array is now in memory. But the value of the pointer that we saved is right here, right? So you see that there's a mismatch between this value and this value. And then if you use that in something, so, just use that, call the square function with that pointer. And all of a sudden we just used memory after free, but we got away with it, and it even seemed to work. And sort of this is like a trivial example. It's pretty easy to see what's going wrong here in just a handful of lines of code. But you can imagine like how much more difficult this would be to find if, instead this was, 6 or 7 layers down in the call stack inside of a whole bunch of like complicated functions, or even worse, it was in some other thread. And having to kind of deal with that sort of problem. So those are bugs that you can you can write in C++, and the compiler is just going to happily compile that program for you. Whereas if you'd express this same kind of pattern in Rust, the compiler would refuse to compile that code. And we'll go through an example of that a little bit later when I have a section again where we'll stop having me talk over PowerPoint slides and actually go through a little bit of code. But anybody have any questions about like how this works or? Okay, cool. I guess I'll just keep talking. All right, so I guess it illustrates, why memory safety can be such an important thing to have. And the other like value that Rust had was performance, right? And so, why kind of focus on performance? Does it really matter when hardware is getting so much faster? And while historically that's been a really good argument, the kind of most recent trends in hardware are such that it's starting to get to be more appropriate to pay attention to efficiency and performance again. So like Moore's law is still sort of working. It's maybe on life support at Intel, who's been stuck at 14 nanometer, their 14 nanometer process for a while. The other major fabs, TSMC and Samsung, are down to, I think the lowest that I've seen is 5 nanometers now. So that would put them quite a ways ahead of Intel. But even if there's a lot of, fair amount of room to go yet, like a single silicon atom is 0.2 nanometers wide. So like, even if you can keep Moore's law going for a little while yet, I don't know, unless the quantum people can come up with some sort of new algorithms, but it's not like we're going to figure out a way of making transistors out of pieces that are smaller than like single atoms, right? So the sort of gravy train of exponential increases is like every exponential function is eventually going to run into a wall, right? But even kind of more importantly than that, there's these other limits that we're running into, like power dissipation and single core performance. So, you can maybe get better single core performance by doing, more predictions and kind of more sophisticated, kind of computations ahead of time, look at the dependency graph between instructions and kind of, tease more out and bigger graphs out and find more things in parallelism and build that into your chips. But, maybe, that doesn't scale forever. And we also haven't been able to increase the frequency all that much. You've been kind of stuck around 4 gigahertz for, basically over a decade now. And power dissipation and heat dissipation is still a pretty big issue now, because you have all these transistors. They're in a smaller, even smaller space. So power and heat and removing that heat are a huge, becoming real big issues. But on the plus side, we have a lot more cores now. So if there's ways of taking advantage of all of those cores, then that can really help us. But also the parallel programming can be kind of difficult too, especially when you have to deal with it at the same time as all of these memory safety issues in languages like C and C++. So, it's not every application where performance is all that important, right? A lot of applications, maybe they're not really CPU bound. And if it takes twice as much CPU, that's not the major cost in the system in the first place. The cost of actually writing the software really dwarfs the operating costs of actually like running it, the power, the data center costs. So, performance isn't always the most important, isn't always the most important factor. But it is still really important at least in some areas, right? Especially in these abstractions. If you keep building abstraction on top of abstraction on top of abstraction, and every single layer adds, a lot more overhead and takes away performance, that can be an issue over time. And so if you can minimize those performance losses, that can be really important in some areas. So does Rust actually succeed at being fast? The answer is yeah. So far, it's been pretty good. So I don't know if people are familiar with the programming language benchmark game. There's this website that collects these kind of micro benchmarks, has a series of benchmarks and tests that it has dozens of languages. People submit their candidates for programs. It's sort of like a competition to see who can write the fastest algorithm in which languages. And so I just chose the best and worst comparisons between Rust and C, and then Rust in another language that it's frequently compared against, which is Go. So you can see in the top left corner, again, let's get the laser pointer. Here we have an area where Rust is actually beating the performance of the native C implementation by a non-trivial amount. What is that? 1 second out of 1.3 seconds faster out of 7 seconds. So it's more than 10% faster. And then down here in more of your worst case, you have Rust being slower, although not by a ton. And if you start comparing Rust against the some of the garbage collected languages and some of the more kind of abstract, a little bit slightly higher level languages, Go is still considered fairly performant, although it does have a garbage collector. But you can see it, in those sorts of situations, Rust will, sometimes really outperform. And even here in the worst case, the slowest Rust program, or the worst program for Rust and the best program for Go, Rust was still faster. So, it comes with all sorts of caveats, right? It's small programs. Premature optimization is the root of all evil. There's lots of different languages that you can compare against. A lot of code isn't performance critical. Not everything is in your hot path, all of those sorts of things. But again, some code actually is. And so in some cases, it's important. So just a couple other comparisons. This result for Rust and Go, it's pretty similar for both Java and JavaScript in terms of the performance. And obviously, if you compare it to something like Python, you get like several orders of magnitude speed improvement. But so here's like taking, in this slide, I picked like the best results and then the worst results. And then this is like an average of all of the tests. I think there's about a dozen or so sort of different tests. And then there's different like data sizes with different tests and that sort of thing. And you can see, like, surprisingly, on average, Rust is actually faster than C, which is, I don't know, I kind of thought that was pretty darn impressive for kind of a new language that, you don't have to deal with memory unsafety. You're not quite as fast as C++, but, maybe it will get there eventually. C++ has some nice things in it that Rust doesn't have yet, like constant generics. Like that's something that's will be in Rust roadmap that it's doing in the future, but that support for that isn't complete now, right? Anyway, and the other sort of thing here is that there's also this relationship between the safety and performance, especially if you want to use like multi-threading. If you want to use those multiple cores, going back to that example that we had from earlier, it can be really complicated to actually, make sure that you have no memory safety problems, especially when you have you know, a really complex code base and a lot of threads and a lot of things going on all at once, and kind of having to do that by hand. So if there's ways that the language can help you, that might help you also write software faster. So again, I said I'd introduce you to some of the people that you know, have actually written the language. So I got a clip queued up. This is Dr. Nico Matsakis, another member of the core team. Is a, you know, PhD in computer science. He worked on the Java, the JIT virtual machine, JIT compilation of the virtual machine at IBM. And so this is kind of a war story of them using Rust at Firefox. And the history of that's kind of interesting. Rust originally came out of Firefox research, started there back in a personal project of an engineer in 2006, got adopted by and sponsored by Mozilla in like 2010, and had its first like stable release was only in 2015. So Rust really is, you know, only about 5 years old in terms of having a stable release. But it was sort of developed in tandem to wanting to solve some of the problems that they were having in the development of Firefox. And so this is a little bit of a war story from Dr. Matsakis about that. So I'll cue up the clip, and you get to have another couple of minutes of relief from me just talking over slides. All right, here we go.
This dog, I don't know who's feeding their dog spinach, but more like this, like Popeye spinach, right? The kind of spinach that, yeah, it makes you really strong and lets you do stuff that you couldn't do before. So let me give you one example from Mozilla where this was true. So we have, you probably can't read that, that's okay. We have recently shipped in a new version of Firefox an extension that lets us render do some of the CSS processing in parallel. So this part that's called selector matching. It's part of the process of displaying a web page, right? And the thing about this problem is that it's so-called embarrassingly parallel, which is actually a technical term. And it means like, it's so easy to parallelize, it's really kind of embarrassing if you don't do it, because it's just a big bucket of tasks that can be done in virtually any order. And yet, this bug was only recently closed, and if you look when it was reported, let me make it a little bigger for you. It was reported 8 years ago, so somehow over 8 years of C++, people, like really knowledgeable people trying to do this, they didn't succeed, even though it was an embarrassingly easy problem to do, right? And in fact, we tried. It's not for want of trying. We tried 3 times, twice in C++ and once in Rust, right? And only once did we succeed. So that should tell you something about what a difference it can make to have a type system on your side, kind of checking things over for you.
Yeah, so Rust was a big part of the kind of advances in the Firefox performance over the last couple of years. They have the parallelizable CSS, and I think they actually rewrote, if I'm remembering correctly, they rewrote a big part of the core browser engine. I think the code name for it is Servo. Was rewritten in Rust. So a big part of Firefox is now been rewritten in Rust. And it seems, you know, like as an outsider, it seems like, you know, I guess it doesn't seem like that difficult of a problem, right? Parallelizing some processing of CSS. But, you know, it's one thing to kind of conceive about how to write a program from scratch that does it. You know, at least conceptually, you could kind of think of how that happens. You wouldn't run into, you know, a lot of conceptual problems. Obviously, you'd, you know, be writing a lot of code, be difficult in that sense. But on the other hand, if you have to make this happen at the same time as you're interacting with a large and complicated legacy code base, and any mistake that you make, because this is in, you know, rendering HTML pages in Mozilla, like any mistake that you made might be a remote code exploit. You know, you're going to be really paranoid about that, and it sounds like a lot more difficult problem. And so, you know, having some safety be proved in the compiler can be really valuable. And I don't know if it's, if it's easier to do that when you have, a lot of different people in an open source, with an open source project. Maybe that, means that the strong type system is even more important, because there's not like a really knowledgeable core set of people that are professionally paid to work on that. So maybe it's easier to have parallelized that stuff in Chrome, but that's just me speculating about what might be easier. Anyway, so I guess to summarize, just from the first portion of the talk, so really the goal of Rust is to be a systems language, something you could write code for a bare metal controller or an operating system kernel or a database engine. You want it to be as fast as C, you want low level control, but at the same time you want to have this sort of system that makes as many bugs as possible kind of be impossible, to have the compiler just refuse to compile them so that you can catch them early or fail fast, I guess, and have better software as a result. So anyway, that's the sort of core introduction, what Rust is and why it's interesting. And then the sort of next section of the talk is to actually look at the language. But before we dive into some of that, are there any questions or things we want to discuss on the first portion so far of the talk? Is everything going okay? People can hear everything. The videos are playing fine?
Yes.
Yeah.
Cool.
Let's see, there was one, I'm just going through a couple of the things in the chat. I think we may have covered a little bit, but I think coming up. Is it safe to assume you'll speak on how Rust achieves some of the desired things that it does? I think that was about the same time as we were talking about dangerous things that Rust prevents.
Yes, yeah, exactly. I got, it's about a few more slides in. Basically, the next portion of the talk is just there's a couple slides that give sort of a quick introduction where you can get familiar, this actually looks like a familiar programming language. And then I've got a couple of examples where we can go through actual code and examples of things that Rust will refuse to compile, specifically because they'll have these sort of bugs. So yeah, I mean, that's a really cool, it's an important thing, right? Because Rust is making a really big claim, and by extension, by telling you about it, I guess I'm making a really big claim, and you want to actually have some evidence, right? So yeah, that's definitely what's coming up next. Yeah, I can't see the chat right now, so if there's anything else in there.
Let's see, another one about linter and compilers. Is it possible that a really good Rust linter could allow the compiler to have a more relaxed mode?
Since it's doing static analysis, a linter could do the same thing.
Yeah, I guess it's I guess the question sort of boils down to, could you force Rust to just trust me, I've got this right, and with some of the lifetime stuff that would otherwise get compiled away. And Rust doesn't actually have that, but it does have an unsafe keyword and unsafe mode where you can do things that do violate memory safety, dereference raw pointers and that sort of thing. So it's not like you're stuck in this model for every little bit of code. And there are sort of ways, you can't just turn off, it's not like a compiler flag to turn off all the linters. But there are quick things you can do. You can write one-liner unsafe blocks that effectively accomplish the same thing. Because, well, for example, Rust has two sets of types, right? There are raw pointers in Rust. You just can't dereference them. And then there's also references, which are basically they get compiled down to pointers, but they have this sort of additional lifetime information inside of the type system. But since they're the same, they actually are exactly the same thing at runtime. If you're willing to call an unsafe function, you can just transmute one to the other. I mean, it'd make it sort of incredibly unsafe to do that, but in general, you'd want to stick that inside of an abstraction that sort of protects someone from shooting themselves in the foot. But it is possible. You just have to do it inside of code rather than like a compiler flag. But yeah. And yeah, we'll talk about that more when we actually have code. Was there other stuff, George? Or
no, nothing. I don't think we didn't just chat about.
okay, cool. Let's see. So yeah, start with hello world, all right? We got familiar function syntax. It's your normal everyday curly braces language. You got statements. The statements end with a semicolon, right? It's just like, it's not so scary. It's just looks like your normal language so far. One kind of neat thing is you have like the last statement in like an if condition gets assigned. So like the number after this statement runs, because condition is true, number will contain the value 5 after the statement runs. So it's something that's a little bit different. You can actually like assign from the outer part of a statement or another statement or a scope. Where you wouldn't be able to do something kind of similar to that, at least not to my knowledge in C or C++, although I do have to admit my knowledge of C and C++ is a little lacking, mostly because I'm definitely afraid of shooting myself in the foot with them.
They stole it from Python.
Stolen from Python?
Yeah.
Cool. I actually like it. I've used it a little bit. And like you can't declare something in advance. Like you can't declare number equals null and then assign it later. So this is like, I don't know. Cool, thanks. I didn't know that.
You can kind of say it equals null with the optionals, right?
Yeah, the optional type, but then it would be a different type. So it would still have a value. Yeah, Rust makes you initialize everything. You're not allowed to have uninitialized anything unless, of course, you are delving into unsafe. If you're using unsafe, then Rust will let you do that. But just kind of more like getting familiar with the language. Here's while loops and for loops. You've got sort of completely predictable sort of array literal. One interesting thing to see here is that this variable is declared as mutable. So by default, any variable in Rust is immutable. And so if you ever want to change any of the values inside, like if you wanted to change a value of A inside this array of A, currently Rust would not let you do that. You would have to have this mute keyword in front of A. So everything is immutable by default unless you otherwise declare it as mutable. But other than that, it's nothing surprising. There's this an iterator system that you can use for loops, just like you have an end array system in C++ and Java and other languages. So, nothing too strange there. The function syntax is also, not really that interesting. Functions, get declared with fn. You have, the variable name first, and then its type, and then here's its return type. So again, nothing too intimidating there. Actually, interestingly, this won't compile because this function has to return an i32 or assigned integer 32 bits. And it's the semicolon that makes this not compile. So if the semicolon wasn't here, then x plus 1 would be your last statement. That would evaluate to an i32, and then that would be its implied return statement. So you could either like get rid of this semicolon and then it would compile fine, or you could add the return keyword, the explicit return keyword in front of this, and then you could get it. And that would also work. More just kind of stuff that's not all that surprising. You got, all of your standard types, but instead of like long and long and short, I just like explicitly says like how long all the different types are, and signed and unsigned. So having that clarity is nice, I guess. You got your kind of modern conveniences for string literals. You can stick your underscore to separate long strings of digits. You can specify byte strings directly, or if you want to work with bit flags, just write stuff explicitly in binary rather than like, I guess, writing in hex and risking making a dumb mistake or something. But one thing that is kind of interesting here is this tuples are a first class type, or something that's used a little bit more often. And so you can just kind of define these arbitrarily. So this variable called tup is of a type. It's just a 3 tuple, and it has a different type for each of the members of the tuple. And so, you just, from the right side to the left side, it's just an assignment. And if you want, you can destructure them this way so that your tuple gets assigned to, let X, Y, Z, and then, this goes to X, 6.4 goes to Y, 1 goes to Z. It's just, something that could be kind of handy in some places. And then structures and methods. So Rust is kind of sort of object-oriented. If you think of an object, this is a type that has data and associated methods that can encapsulate the data. Rust does have that. What Rust doesn't have is inheritance. So there's no like inheriting from a parent class, and every child object is also of the same type of the parent. So classes sort of mix those two concepts of the interface inheritance and implementation inheritance in a way that can get sort of complicated, at least in some cases. And then Rust treats these as always kind of two separate things. So you can build very similar structures as you would with classes. Rust just forces you to be explicit about it. So you have to do it with composition rather than inheritance. And I guess in some places, like in those GUI toolkit classes that, are like 10 layers deep with inheritance. Maybe there'd be a lot of boilerplate code and sort of annoyance dealing with that. But, there's more than one way to do it. There's more than one way to do a lot of things. So, yeah, you can still accomplish kind of the same goals with this system for the most part. But on the other hand, Rust does have interfaces, like Java or C# have interfaces, or something very close to it. They're just called traits. Structures don't have inheritance at all, but traits can have inheritance. So like every object that, so if we have every object that has a summary trait, we could have another a trait that would inherit from the summary, and then everything that inherited from that sort of child trait would also be of the parent trait. But that only works for traits and not structures. And then you can, with those traits and generics, you can use static dispatch and templates. So like C and C++, C++ really, it's going to get reified, or actually turned into, specific code is going to get generated for each type once that actually gets compiled. Or Rust has a dynamic dispatch too, so that you can call, you do like a virtual function call. But there are more restrictions on the types with that. The difference between traits and an interface, at least so far as I can tell, is that you can implement a trait on any type actually, and that not even just your own types. So that means you can implement traits on types that are in other libraries, like even in the standard library, or even core types. The rules are just that the implementation, if you're going to have a type implement a trait, either the type or the trait has to be in your code, in your library. But as long as one of those is the case, you can implement that. So what that means is that you can write your own trait, and you can have a standard library type implement that trait if you write the implementation. Or if there's a standard library trait, you can implement that standard library trait for one of your types. But you can't implement one of the standard library types or one of the standard library traits on one of the standard library types. So there's just, there's a certain limitation there where you're not writing code that's sort of outside of your library one way or the other. And that can prevent conflicts. It gets a little bit complicated more when generics are involved. This is kind of one of those pain points of Rust is when you start interacting, having some traits interact with each other, things can get kind of complicated and the rules can get complicated, and it takes a little while to work out exactly what the rules are. But this is one where I'm not going to go over those rules right now, but just to allude to, some of that complexity is there. But we could talk about it if anybody has a specific question. Rust also has this enums, this kind of algebraic data type where there's this one type, but it has these different variants. And so it's essentially like a tag union. So in this example, like quit, move, and write are subtypes, and they can each have their own sort of associated data. Like quit just doesn't have any data associated with it. But if the message is, if it's a move variant, then it's going to have this X and Y variable that you can get out. And the same thing, if it's a write variant, there's a string you can get out. If it's change color, you get, those variables out. And at runtime, this compiles down to there's a selector that tells you which one of these you're on. And then the rest of the type stores this information. But it doesn't store them in sequence. It stores them over top of one another, right? So the memory that would normally contain, X and Y, if this were a move variant, gets overwritten by a string if that variable gets changed to a string, or gets overwritten by this set of I32s if it gets changed to that type. And then the size of that is the size of the largest variant, because it's got to be able to fit everything in there. But it's kind of interesting because, anything you can do with the structure, you can do with an enum too, like implement traits if you want to. But then along with the enums is matching. So there's this sort of match keyword where you're matching on this variable that is an enum, and then you have to list all of the types. And for each type, you have a different block of code that can run. And if each one of these had different kind of variables inside of it, you'd be able to access those, you'd specify those variables here, and then you'd have access to them inside that block. And then there are kind of two really common enums that are really useful. One is option, and the other is result. So option is basically the same thing as you'd have in Java, where it's either some and it contains a thing, or is none. And that's really useful because it means that you will never have a null pointer exception, right? Because when things get returned as an option, you have to unwrap it from the option. You can't get at what's inside that option without writing the code to do that. So, the whole concept of having a null pointer exception isn't really possible in Rust because of that. And similarly, result is a very common enum that's used for returning, unsurprisingly, returning results from functions. And it lets you deal with either the OK condition or the error condition. And if you call a function that, it's going to return that result, it might return an error, Rust will make you deal with that. If you don't deal with it somehow, you can't get at what the result was. So it will refuse to compile unless you kind of deal with that somehow. although result has this kind of really cool language support thing where there's this question mark operator if you know, the error that you're going to get is the same that you would return, that, you know, the function that you're in is going to return, it'll let you use that question mark operator and it would just kick that error up a level, up the stack a little bit. So it's sort of like the equivalent of an exception that you can write really quickly without a lot of boilerplate code. And it, you know, has that because it, you know, the language itself knows about the result type. And so, you know, like C++ is sort of really, you know, cool thing about some of these abstractions is that, you know, Rust tries to build them in a way that they have little or sometimes even no cost at runtime after they're compiled. So an example of that is this like option box and then T. So box is just a type that means the allocation is on the heap. And then option is just a type that, you know, you either have something or you don't. Whereas normally, like, you might return a raw pointer in C and you'd have to check, well, if the pointer is null, that means that there was no object returned. And so you'd want to do that null check. And then otherwise, if the value was some valid pointer, then, well, you know, now there's a valid object there. And now I'm going to, you know, assume that's an object and assume that everything was successful. And, you know, the C obviously is, I mean, it's, you know, you have to do that manual checking, but you have the advantage of having it in just that one, in one number, right? It's just that one number of that pointer that gets returned. But that actually is how option box gets compiled down, because inside of that option type, or inside of the box type, sorry, the pointer is of a special type that's non-null, which excludes 0 as a possible value inside the actual type system. And so what that means is that when this compiles down, it compiles just down to a pointer. I mean, you get exactly the same thing as if you had written the code in C and actually done the check. So you don't actually have to pay anything for that abstraction at runtime, which is really nice. So you get the safety and kind of the compiler checking your back, but you don't have to pay that cost at runtime, which is, you know, the kind of the whole kind of thing that Rust is trying to do. So obviously not like every abstraction has 0 cost, but, you know, it tries to, you know, minimize those sorts of costs where it can, and sort of only pay the cost when you actually have to pay the cost. So, and then the kind of major, the most important way of doing that is with lifetimes, and we'll kind of get to that next. And so I've been talking for a while again, just over slides, and I thought it would be nice to take kind of a change of pace break and actually look at a little bit of code for a while. So were there any questions that we want to address from these slides before kind of jumping into a little bit of the code demos? Again, noting I can't see the chat questions, sorry.
I was answering a question on Slack and didn't notice the chat until way too late, but let's see if there is. Pub means public, right?
Yeah, yep.
Cool. And I have no idea where the other question is referencing because it's probably some code lines somewhere. If you had more lines before the last line, they would have semicolons, right?
Yes, yep.
Okay.
Yep, I know what that's referring to.
Okay, the lack of semicolon tells what the return is. Okay.
Yep. All right, so I'm going to stop the screen share of the presentation, although I'll come back to that later. Oh, look, there's the chat. 17 messages. Oh, I wish I could see that at the same time. Oh, you know, I forgot there was like a way of doing that inside the Google Slides that I'm presenting, but I forgot to turn it on. So maybe I'll do that for the rest when we go back. But I thought I'd do the screen sharing for a minute and tap intro to Rust.
Does the allowability of no semicolon at the end mean that semicolon is a statement separator versus terminator?
Separator versus terminator.
Well, like in JavaScript, it's a separator, and in Java, for instance, it's a terminator. So you have to have every statement in one fashion or another end with a semicolon.
Yeah. I mean, that sort of sounds like it could be right, but I don't know enough about the abstractions and like the technical definitions to like give an answer that would, I mean, be that I would have confidence in one way or the other. But yeah, in general, you need like you need the semicolon to separate out stuff. And when you don't have a semicolon, it's usually because you're returning, well, it's because you're returning a value up some scope. Either it's from an if statement or a match statement or inside of a loop or something.
So maybe.
All right, let's see, I'm screen sharing. Oh wait, that's not what I wanted. I just shared the presentation again. Intro to Rust, Google Slides, Intro to Rust, and Sea Lion. This is what I wanted to share. All right, there we go. That's better. All right, can everybody see this? Is it like high res enough to actually read code, or is this like a fool's errand that I can make this work? Okay, I see at least one thumbs up.
I can read it. I usually recommend one more +1 on the Zoom. Because when this recording gets shared, you don't know what the screen size will be that they're looking at.
Maybe if I make it a little bit smaller on my screen. Is this better?
That's better.
Yeah, I think that.
Okay, cool. So I got my sort of list of demos here. Just a couple things I thought I'd go over that are kind of sort of neat. This matching thing, this match tuple function, is you can be kind of sophisticated with what you're doing with this match statement. As long as you have an exhaustive list, you can match like, here's where, I don't want the documentation. Go away, documentation. Where the different members, the first value is of this type or is of that type in the enum. You can match on the values inside the enum. As long as you can make sure that everything is exhaustive and always return something in the best case or in every case. And you can use some kind of sophisticated match statements, and that can be kind of fun and useful in some cases. Compiles, runs. You can match on ranges. There's this right here, this syntax, this if let sum equals is a way of getting something out of option. So, this if condition will only trigger if, what's in this option variable is actually sum. And then here's the value, and then you can have, the value inside that if statement. And then here's just like an example of the, I was talking about that result type where you can use a question mark operator to like, short circuit, like dealing with all the error conditions if you want. So, this function might error. Can I just make that go away? My error returns a string, and so does the function that it's being called from, right? So the error in both cases is it's string here and it's string here. And so if that's the case, then I can just use this question mark operator. And if this function errors, if this line would produce an error, then just shorter this way will return with an error. That same error will get kicked up a level. Just smart pointers thing. So ranking this a little bit of syntactic sugar makes the medicine go down. So they're like, kind of these, special types or abstractions. Boxes one, it's just like a pointer to the heap, or there's others that are like pointers that are behind mutexes and stuff. And it's kind of nice that Rust has some syntactic sugar where you can just kind of like refer to it as a pointer, like as a smart pointer, and it will take care of like finding the trait that dereferences it for you. So there's this deref trait. You can implement it on your own types if you want, but it lets you just use this dereferencing syntax with a star like you do with any other pointer. There's some sort of quality of life things, like here you can see there's this kind of standard traits. And so if you had to write every one of these traits, you had to write a debug implementation, you had to write a quality or partial quality, it'd be kind of a pain in the rear just to do all that. And so there's this kind of quality of life of just, like writing a lot of that boilerplate for you. And so like it gives you this nice, automatically will do a nice debug format for you. All right, and then here's the lifetimes demo. This is kind of the heart of it. So this no mutable aliasing demo, this is basically exactly the same thing as we did in the C++ example, right? We have a vector, we reserved a certain amount of capacity, we're filling up that vector, we're taking a reference to it, we're saving a reference to it. And so, this line, this is a reference to the third element of vector v, right? And then after I'm taking this element, I'm going back to this vector and I'm going to, push more values into it, which means I'm changing it. But then in Rust knows that you've done this. And if you try to use this variable that you've taken, if you try to use reference after you've already used it in a way that you're changing it again, if you've also borrowed it mutably is what it's called, Rust will complain at you. So there's this print line, all I'm doing is basically the same thing as I did in this line. I'm just doing it after I've made these changes. And so, if I try to compile this, Rust is going to give me a compile error. And it's kind of this friendly compile error where, this has historically been kind of, difficult. So Rust goes out of its way to kind of make a nice error where it tells you, well, you immutably borrowed it here, and then you mutably borrowed it here, and then it's basically telling you exactly what you did wrong. So Rust is saying, you can't compile this, and here's some help about, what you did wrong. So, I mean, that's the example where if this was C++, we just have shot ourselves in the foot where we'd be using after free, and Rust kind of stopped us from doing that. And it did that because of the lifetimes and these rules on mutability and aliasing. It's like you can have an alias or you can have pointers to things. And if they're read-only pointers, you can have as many pointers as you want at the same time. But if you have mutable pointers, pointers are going to change some state. You can only have one of those at a time. Unless you go through some kind of fancy unsafe stuff where you're locking. You have to go through mutex basically to get that in two places at once. And if you violate those rules, Rust won't let you compile. So in this case, we have both a mutable reference and an immutable reference at the same time, and that's not allowed.
Karen, I think I've seen somewhere that if the compiler does complain about that sort of thing, one of its saving graces is it gives you really good error messages like, well, here's what you could do instead.
Yeah. Yeah, because like if you don't, I mean, when I was learning this the first time, like this was kind of a new concept for me to learn. And so, yeah, it can be kind of difficult, and having the compiler be friendly, it was really nice when I was learning Rust to have those error messages that were kind of pointed out, not just that I did it wrong, but how, and kind of making suggestions for how to fix it. So the lifetimes and the lifetimes being embedded in the information in the types. So like here's a structure, and the member of that structure is a pointer to a string. And so in order to define this type and have it compile, I have to be explicit about the lifetimes. So this generic, tick A is a lifetime. And what that's specifying is that there's a lifetime for this pointer. So, and then there's a lifetime for this structure. And what this is saying is that this, any instance of this structure A, it can't live longer than the string that it's borrowing, right? Because it borrowed the string. And if that string goes away while you still have a valid copy of A, well, then now A is pointing to nothing. And so that's what it wants. That's what Rust wants to prevent. And so, if you're going to have a structure that contains a pointer like that, that pointer has to have a lifetime. If I take out, this information, that type information. I try to compile, again, Rust would say, we expected you to tell me explicitly about the lifetimes there, and I'm just not going to let you compile it without having that lifetime limitation in there explicitly. And so this can get a little bit complicated sometimes. So say, this A class is like a parser, and we're going to take a string and we're going to parse it. In this case, I'm doing something really simple. I'm just removing the end of the white space. So I have this message. It's just SOS with a couple of spaces afterwards. I'm going to stick it into a variable called bottle, which is of type A. And the string is a pointer to the string that's inside. So it's a pointer and a length, just a very kind of simple type. And so if message would go away, as long as message is valid, so is bottle. So I can write, I can run. Oh, what did I not fix? This is going to be a problem if I don't go back and, okay. When I break things, I got to fix them before going on. So as long as message is around, this bottle works. This bottle is valid. But as soon as I drop message, as soon as message is no longer valid, if I would try to compile this, well, now it knows that bottle is no longer valid either, because this lifetime that it was depending on is gone. Message isn't around anymore, so Rust knows that bottle is no longer valid, and isn't going to let me access it. So that won't compile. On the other hand, since this is a parser, I really should be able to have a string that outlives the parser, right? Because what I'm ultimately borrowing from, the data that I'm ultimately pointing at, is from this source string. It's not actually from the parser itself. So here I've got trimmed. So trimmed is this sort of post-parsed. It's got, it's actually just SOS. Currently, the way things are written, it won't let trimmed outlive the parser, or it won't let it outlive bottle. So if bottle gets dropped, if the parser gets dropped, it'll refuse to compile, because bottle is no longer valid, so my trim string is no longer valid. But that's just because up here, where the lifetimes are specified, or where this parse function is, the lifetime of the resulting string, see now it's not specified here, but it's elided, and so it's just omitted to make things look different. But what's really going on here is, you could think of it like this, is that B has a life, or self has a lifetime. And in this case, it's referring to the lifetime of your pointer to A. And it's saying that the string that gets returned can't outlive self. That's giving me an error because B isn't in the template here. But now that's valid. But my IDE is giving me lint because it could just be elided. It could be removed. But this is actually kind of a different situation, because what I can do is, the lifetime of the string that I'm returning isn't ultimately dependent on the parser, right? Like I was saying before, the data that's in is actually from string. So if I want to be able to do that, and in some cases it's important, like if you're actually writing a parser and you want to have references to stuff that's been parsed, especially outlive the parser, what I can do is I can specify in this function signature now that this lifetime of this thing that I'm returning, it's not the lifetime of A, it's the lifetime of this string specifically. It's not the lifetime of my reference to A, it's the lifetime of that string. So now that I'm returning directly from this string, now if I remove bottle and I have this A here instead of it assuming the other thing, now it will actually compile and run successfully, because I've told it where the lifetime is coming from, and I've connected it to something that it can prove exists. So I know that's sort of complicated. Is that kind of coming across okay, or this is probably a good time to stop a little bit and talk about it?
I feel like I'm going to watch that over and over again on the recording.
Yeah, this is was something that's kind of hard to get. This is a little bit more of the more like advanced lifetime stuff. Like when you don't have something that's like super simple. One of the ways that Rust is kind of difficult to learn is that in order to make things like easy to write most of the time, it does a lot of this like eliding lifetimes or just like automatically doing the right thing. And that's really cool in some cases, like when you're learning the language, because it means you don't have to deal with the complex stuff. But it also means that like when you do want to do something that doesn't fit and is a little bit, doesn't fit with a simple example and is a little bit more complicated, now you have to kind of like go back and figure things out a little bit. And so that's kind of one of the like, kind of pain points in the steeper learning curve of Rust is like all of a sudden I realize I have to deal with this complexity that I didn't have to deal with before. And I thought I understood this, but I really didn't. So,
lifetimes it's just a new concept.
Yeah.
Right. I haven't done anything like that.
Yeah. And Rust really kind of pays you back for like actually, like reading the book and like learning about these concepts a little bit in advance. Like in a lot of other languages, it's easy to just kind of stumble through because, so many languages are just very, very similar to each other. It's just like, the syntax is slightly different or the standard library is slightly different. But for the most part, you can kind of stumble your way through like reading through code in Stack Overflow and it's, fairly obvious what things are doing. And Rust is one of those times where it's not always like that, where sometimes you got to kind of go back because there are new concepts that aren't in other languages and that people don't have a lot of experience with. And that's where that sort of learning curve that, Steve Kalibnik in that first presentation talked about that being one of the pain points. Like, this is what you want your cake and eat it too. You have to kind of deal with this extra complexity too. Like you have to deal with this hard part up front, but dealing it with up front is in the long run is really better for you.
So to that point, how well do design patterns translate? The design patterns we all know and love or, can apply in a lot of the different OOP languages or whatever the case might be. Do some of them apply here? Are others just don't work, et cetera?
That is a really good question that I have not thought a lot about. I think a lot of them you can probably make them work. You'd have to figure out. Basically, you have to figure out how. Like, I don't think that there's anything in the design patterns in general that are unexpressible in Rust or that Rust would prohibit, because Rust is mainly concerned about preventing you from doing unsafe things. It wants to prevent you from screwing up memory safety without kind of ditching to the unsafe keyword. But is generally you can express most patterns. I think you'd be able to do most things. Now there's like some standard library, there's pieces of the standard library that you might have to use to make certain things work. But if you want to have basically something that's the equivalent of a Java type, right? Where it's like mutably shared between, it's on the heap and it's mutably shared between all sorts of threads. You can actually have that in Rust. You just need to go through, your type has to be atomic reference counted. So like it has to know that it's being shared so that it uses atomic instructions for the reference counting. And it has to be behind, if you want multiple threads to use it, it's got to be behind a mutex. But Rust has those sort of abstractions that let you do those things. Those abstractions are built out of unsafe code. But if, you can do things that would otherwise be unsafe if you're willing to use these kind of standard types, and they're marked as such. So it's not that Rust prevents you from doing anything per se. Like I haven't run into anything that I haven't been able to express. But it's going to make you think about it a little bit sometimes, and figure out like, what's the right, Rust abstraction that I need in order to do this.
Sure. So the patterns hold up. It's just how you do it and working yourself out of potential even issues that you might get yourself into with some of the other language. The pattern is the same, but how you do it, you have to kind of rethink. Makes sense.
Yeah, exactly. So, I mean, like if you want to do a singleton, like, a singleton is an easy pattern that's like, it's trivial to do in like Java or C#, right? You just like assign something to a static member of a class. Mm-hmm. And Rust is a little bit more complicated than that, but there's a nice abstraction that people have built as a library. And so you can just use it's called lazy static is the name of the crate or the Rust library that does that, and just provides kind of a nice, relatively simple way of doing that. But again, you have to find the right abstraction, and the right kind of library code. But that's sort of something that you have to do in a lot of different languages. That's not necessarily unique to Rust.
Yeah, like one that I think would be a couple that I think could be a little bit different, right? Like in Rust, you can't do inheritance, but you can compose.
Right.
Right. So that's probably going to mess up a few patterns, but also give you a lot more flexibility to do other things. Also, being able to like add implementations to existing types kind of flips how you would do the facade pattern, right? You just say this one type is now, it can do all of these things. So I don't need that extra thing to provide that unified interface.
Mm-hmm.
Yeah. It's a really good point, though. I mean, like, that would be a really interesting thing. I wonder if anyone has done that yet, of going through, like, like writing a blog post with, like, here are, like, the, 20 most popular design patterns, and here's how you would express them all in Rust. Are they just simple? They require something complicated. They require a library. That'd be really interesting. Like, I wonder, it seems popular enough that, like, I wonder if somebody has done it already. And so if we do a Google search, we'd find it. But it would be a great idea for a sort of a blog post or something. Nobody's done that yet. I mean, that's another kind of interesting thing about Rust, is because it's new, it's like not everything has already been done by somebody. And so there are positives and negatives to that. And, like you can write, if you want to contribute, like you can write a library that people will use, because there's not like already 5 libraries out there that do the same thing. But at the same time, like the trade-off of that is like, maybe there's not a library that does exactly what you need, that might already exist in a more established language like, Java, where there's just every possible thing is available in some library or another. Okay, so we'll move on a little bit. So we also talked about like that Rust will prevent data races for multi-threaded code. And this is like another potential source of unsafety, like memory unsafety, and these like really pesky, thorny potential security bugs and crashes that had prevented Firefox from doing their parallel CSS styling. And that's another kind of major feature of Rust, is that because of the way that I don't know why my screen is my Zoom is going a little crazy. I'm sorry, I'm distracted by that. Because of Rust type system and this sort of extra information that you have, Rust can basically prohibit this simultaneous aliasing and mutation without locks. It can do that also across threads. So as long as you stay in safe Rust and are just using like standard library abstractions and that sort of thing, you can kind of get safe abstractions. It can be provably safe in a multi-threaded environment where, I mean, you can't like totally eliminate all race conditions ever, because there are maybe some conditions that are outside of your machine, but you can at least eliminate those conditions that would be like memory or data races inside the machine. So you don't have like memory unsafety as a result. And so I kind of coded this like little simple example, lifetimes and threads, that kind of gives a little bit of an example. So this is another way in which we could like just really shoot ourselves in the foot, right? If this were C++, basically what we're doing here is we're just allocating a variable on the stack, in this case just a number, right? Because we want to keep the example as simple as possible. And we're spawning a thread with a pointer to this variable, but this variable is on the stack of one thread. It's on the stack. So if we would do this in C++, like we'd spawn this thread, and then this, and then imagine there was nothing else here, right? Imagine this was all commented out. So it'd spawn this thread, and this thread would reference something on the stack of this function, but this variable is going to go away as soon as this lifetimes and thread function returns. So as soon as if we write code like this, we'd instantly have a multi-threaded unsafe condition, like if we were writing this in C and C++. But
quick question from chat. Line 147, the curly brace, colon, question mark, curly brace in the print line, in the string.
Oh, right. This is just the debug format for, I don't know why I even put that in there. That's, there's like a debug print and then a normal print, and like just the curly braces inside of a print line statement just does the normal print, which works for an I-32, but a lot of types don't have like the display type. So I just kind of got used to always writing the colon question mark. And that always outputs the debug string. So
Thanks.
That's just why, like anything inside those curly braces gets fixed by this. And this is actually a macro, but there are only so many things I could talk about. Rust has a really cool macro system, but actually a really powerful macro system that you could almost think as compiler plugins. It's that level of useful and powerful. But your talk can't go on forever. I suppose you got to figure out where to cut somewhere. Oh, let's see chat. Oh, fantastic! I can see the chat. The bang is pretty much like a template, literal. Yeah, like a spot where something fits in the template. Yeah. Yep.
I think that's for the print line exclamation point.
Yep. Okay. So I guess the thing I wanted to demonstrate was here I wrote, radically unsafe code, and Rust is going to complain and it's not going to compile it for me. And it's going to tell me why. It's going to tell me that number is borrowed, but that the thread outlives the value that it's borrowing. And technically this is a closure, not a function, but Rust has, lets you do functional stuff too. But so it's, Rust is going to be kind of picky about this multi-threading stuff too. But on the other hand, like we were talking about earlier, it'll actually let you do stuff if you specify the right abstractions. So right here, it's going to let me, in this case, these two lines, I've actually, not only have I allocated the value on the stack, or sorry, on the heap, because anything that's inside of a box is allocated on the heap rather than the stack. That's what the box type is. And then I'm not borrowing it. I'm not letting this thread borrowing it. I'm actually moving it. So if I were to try to use number after this, like number, like we'll try to add 1 to it. Like, and if I try to compile this, Rust again would not let me do this because it is, I've already kind of given this to that thread, and now I no longer have access to it. It's also complaining because it's mutable and I'm not trying to change it. It's complaining because it wasn't labeled as mutable, and here I'm trying to change it. But even if I would solve that problem, it's still going to complain about, here's where I moved it. It's helpful. Rust is telling me that not only that I've done something wrong, it tells me that when I did a different thing wrong that I thought I was doing wrong. So yeah, it's being really helpful. It's telling me I'm moving it here. Value was moved into this closure, and now I've used it after I've given it to someone else. So now this has ownership of it, and it's no longer mine to do anything with. All right, but the next thing was like if you actually use the right abstractions, so we have the atomic reference counted pointer here, and inside of it is a mutex, because we want to have mutable access across multiple threads. It's going to let us do this because these types kind of take care of that unsafety for us. It's going to make sure that only one thread at a time can lock the mutex. And so if I actually run this test, run the times demo. Okay, it's not showing up in the test because everything was in a different thread, so it's not showing up. Oh, there it is. Okay. So here's all of the output from all of my threads. All right. So I just basically, I spawned 100 threads here, and each one of them, depending on whether the iterator that I used to create it was even or odd, I had to increment or decrement a counter by one, a shared counter across all these different threads. And, because it was in a mutex, Rust let me do it. And then, here's every different thread printed it out to standard out. These negatives are when it, dashes are from when it went negative. But then you can see like total is 0. Like there was no case in which, there's 100 threads banging on a 48 thread machine, right? Kind of all at the same time. There was, because this is all atomic reference counted and with mutexes, there were no sort of reads and writes that were unordered. Like Rust made me do it the safe way, basically. So, I mean, that's really kind of the demo. The real core, like value proposition, like the thing that Rust does that other languages don't do, and the thing that makes it so kind of interesting and powerful, is this lifetimes immutable aliasing stuff. Like nothing else that I know of does that. And, that's what gives you the memory safety without having to have a garbage collection, which is kind of cool.
What's the compilation hit to all this?
Yeah, so that is a frequently cited pain point. It's not super fast at compilation.
Okay.
But it's not like it takes a super long time either. Like if you're doing development on a single library and you're just, kind of doing incremental compile and it's not like an optimized compile, it's just like, a debug version compile. It actually goes pretty fast. Like a compile, I guess I don't write that big of a project, but it's nothing that takes more than a couple seconds. Certainly under 10, usually like 2 or 3. And you can also, there's like a check version that does all your syntax check and linting without actually doing the code generation. So you can do just that step, and that step is really fast. That step happens almost instantaneously. But yeah, the compilation has kind of been cited as a little bit of a pain point.
Gotcha.
Because it does have to do with all these extra checks, right? It's going to do all this static analysis at compile time.
That is the reason that I asked about the really smart linter idea, because if you can take a lot of the model that the static checking in Rust compiler is coming up with and push that shift it left, so to speak, into the linter, then that responsibility with some kind of a safety check that says, this was processed with a linter that makes it unnecessary to do all the same things again in the compiler.
Yeah, that's sort of a good point, right? You have to do the checks over and over again every time it compiles.
Yeah. And if you left, so you're doing it and you catch it real time, like that's what a linter typically is doing. It's giving you a little red squiggly underline, say, hey, pay attention, this is wrong.
Yeah. And like I wonder, like I don't have a ton of experience working with like really extensive tooling in C and C++, but I would imagine, like I've heard that there are tools that do that sort of static analysis for C and C++, or that try to do it and do end up catching a lot of things. Maybe not as much, or it's not as integrated in the language as it is with Rust, but.
What's the refactoring support like in this tool, this CLive that you're using?
Yeah, CLion, it's just the IntelliJ version of stuff. The refactoring support is actually quite good. So you can do like the quick renames. If you want to rename a type, that aspect works pretty quite well. I think it just added support for like being able to move types around your kind of hierarchy and doing that sort of refactoring. So like if you want to move a module or a type up to a parent module or something like that, I think it added that support relatively recently. The Rust plugin for CLion has been quite active. Active development, actually. There's a new patch that comes out every week or two where they're kind of constantly adding features. Another thing that they're doing is like macro expansion. So the whole macro system, like not only is it usable for functions, but you can like use macros to like automatically implement traits, or have, you can do a lot of code generation really with the macro system. And so CLion also will like go through that, like it has an internal engine that like expands all of those macros and adds all of the generated code to like the autocomplete, which is really useful.
Question in chat, what is a mutex?
So mutex is mutual exclusion. So a mutex is basically like a lock for some data. So there's only one thread that can have a lock at any given time. So if one thread has that lock and another thread tries to access the same lock, there's either two choices you can make, usually depending on what functions you call. You can either like have your thread block until the mutex becomes available, like wait for the other thread to be done with it and then continue on. Or you can say, well, if someone else currently has this lock, just let me know that it failed and I'll figure something else out. I'll fail or something. But yeah, the mutex is like it's like a protection so that, or a lock, so that you can only have one thing accessing it at a time. So you can have that be like really coarse grained. So it can be like a large data structure. So you have access to that large data structure is where the lock is, and then you can access all like the little bits underneath it. Or it could be something that's a little bit more fine grained. I guess exactly where you'd put that would be like a design question about, what's more efficient and what do I need to mutate versus what can I just share and it doesn't change, that sort of thing.
That's a favorite interview question. So a lot of companies like adding that into their trivia question section. So.
Okay. Cool. Well,
I'd also recommend looking into semaphores.
Okay. Another good like interview question. Like have a nice good answer for that. All prepared and ready to go.
No, seriously. I can't tell you how many times I've been asked to describe what a mutex is, compare and contrast against semaphores, talk about how to deal with thread locking. It happens all the time. And I would love for somebody to answer, use Rust. I think that would be hilarious.
Who cares? Use Rust.
Yeah, right. My type system does that for me.
And I'm seeing you using like tests. Is that, I'm assuming that's a separate crate or something, or is that actually built in?
Okay, so that is actually built in. That's part of a system called Cargo, which is like the package manager for Rust. It's sort of like Maven and Make and CMake or something, kind of all rolled into one.
And it's
if you're familiar with Java. What?
And it's part of that. It just comes, it's not like JUnit where you have to, it's a dependency you need to pull in, or is it part of, you do have to depend from that cargo dependency,
Right.
whatever the case might be.
It's part of, so cargo is like, it's part of Rust. It's the Rust build system. So like you don't have to specify it as a dependency. Cargo is what you use to specify all of your other dependencies.
Okay.
And so cargo will go out and it will fetch everything from crates.io. It will pull it down as if it were from, the Maven repository or the node.js repository or whatever.
So I bet this would be a really popular talk for the 42 mentors on exorcism that are all Rust focused. You'd have a built-in audience.
Well, that's cool. And there's there's a lot of like really great talks on this online, right? Like, so I'm providing an overview and like, I'm interactive, right? So it's kind of nice to be able to ask questions and stuff. But there's a lot of really cool presentations and stuff online. Each one of them is an hour long. But if you want to see like some of the creators of Rust, like give what's essentially like a job talk to the CS department at Stanford, that talk is on YouTube, which is wonderful. So it's like all these CS professors that are asking these questions that go way over my head, but it's kind of fun to be a fly on the wall and see, like, how do they answer this? Then look up what the heck that is they were talking about. So. There's just a little bit more here that I have to go through with the actual code part. So I have this kind of module function demo. So it's just like, Rust has, support for functional programming. Here's just an example of, things get a little bit more complicated when you're using generics. So this will like repeat a function as many times as you want. Little 5-liner that I wrote is generic, right? So, it takes any type as an input, type T isn't bound. And then it takes this closure as function. And that function or the type that you pass here, it will work for any type that matches this where condition. So as long as it's a function that takes an instance of T and returns back an instance of T, you can use that with this repeat function. And it will, of course, reify that by actually, plugging in the code when it actually gets built into machine code. That's just an example of, you can do a little bit more complicated stuff with generics. I didn't want to have everything be, completely simple. And then I had this kind of fun, like little safety demo, right? Where I had this function that I lovingly called the Leroy Jenkins function. And so what it does is it just uses a random number generator to generate a random 64-bit unsigned integer. And, inside of this unsafe block, it just dereferences it. So this is just, using some random pointer to read from some random memory address. You can do that as long as you're inside of this unsafe block. So Leroy Jenkins is just going to attack some random address and is going to crash the whole process by doing that. And then maybe the more interesting thing here is this Typhoid Mary function. And that is, you have to be careful when you're building, or you can use unsafe to build abstractions that are supposed to be safe. So, here's, this example is Typhoid Mary. All this function does is it just takes a raw pointer and dereferences it. It doesn't dereference it. It just changes it into the Rust type that's used for references. And this specification of the static lifetime here just means don't worry about it. It's always valid. It's valid for the life of the program as long as it's possibly running. You never have to worry about this becoming invalid. That's what that static lifetime means. And so, Typhoid Mary basically is is writing a check that it cannot possibly cache. And what happens there is, I've returned this, when I call Typhoid Mary here, it's taking this pointer and it's returning this thing that I can actually call in safe Rust code, but it's not actually safe because it's really under the hood, it's just a pointer, and it's still pointing to a random memory address. And so if I, had written this wrong, now I'm not in unsafe code here anymore. I can still blow up the program. So the point is, you kind of have to be careful about, when you're building these safe abstractions out of unsafe code. It's possible to screw up. It's definitely possible to do things dangerously. Let's see, other questions. What's async stuff like in Rust? I haven't worked with it much myself directly. From what I understand, I've looked into it a little bit. It's fairly new, and people are pretty excited about it, I guess. It recently got released in the standard Rust, so you no longer need like nightly builds and that sort of stuff to run it. But I haven't personally used it. I know that it's out there and that it's pretty popular. In fact, when I go back to the slides, I got like people some examples of people using it, like Dropbox rewrote this core of their sync engine in it, and they use the async stuff to do that. On Rust to Wasm, yes. Also, Rust uses LLVM behind the scenes. So any target that LLVM can compile to, Rust can compile to. So you can target microcontrollers, anything that LLVM supports, and that includes Wasm. So I don't have a lot of experience with that. I know that it's a thing, and I know that people do it. There's a whole working group for it, but one person only has so much experience. Can only kind of get experience in so many different areas, I guess. Wasm seems like a really cool technology, though. Anyway, okay, so that was all I had for the code portion. Let me see, we are actually like coming up on 2 hours now, so I'm sorry if it is a little longer than I thought it was going, but that's always the case, right? Everything always takes longer than you expect.
Oh yeah, no, I generally tell people, if you think that you're going to go too short, you're wrong. That's literally never happened.
See, share screen. I'll go back to my slides. All right, can you see my slides again?
Yes.
All right, cool. Go to my presenter tools. So a couple of these slides I kind of replaced a little bit with the code talk because I wanted to do something a little bit different. I just kind of listed these sort of 3 types of ownership or ways of accessing data. Like one is you own something, you can do whatever you want with it. You can change it, you can destroy it, create it, destroy it, whatever. It's just going to get deallocated when it goes out of scope. There's a mutable borrow. You can have as many of those at the same time because everything's just sharing this sort of read-only thing. There's no memory unsafety that's inherent in that. But when you have a mutable borrow, that's where you have this restriction where you're only supposed to have one of those at the same time. And so this is sort of core problem, like mutability, simultaneous mutability and aliasing is the cause of a lot of these memory unsafety bugs. And so that's really the major thing that Rust is trying to prevent from happening. And so that can be, we talked about the data patterns and how you can express most things of the data of the design patterns. I think you can express, but there are some you can't express a doubly linked list that way. It's kind of like the canonical example of something that should be simple. It's simple in a lot of other languages, but for some reason it's really, really difficult in Rust. And that's definitely true. There are definitely ways to different data types and ways to express your program that Rust has a really difficult time with. And so often, maybe the best way is just kind of work around that and use some sort of different abstraction. Maybe you absolutely can't, and so you have to deal with the sort of difficulty of working with it that way. But there's like a whole how-to about how to how to learn Rust with entirely too many linked lists. Because this is sort of like a famous example, like Rust is great, but you can't even write a doubly linked list. It's so restrictive. So, I mean, that's definitely a thing. There can be some patterns that are really difficult to express. And yeah, so there's also this rules are awful and I need to break them, this sort of Dr. Horrible. If you've seen Dr. Horrible's sing-along vlog from a couple of years ago. Anyway, but Rust, gives you some of the abstractions that you need to deal with that. The box type, the atomic reference counting, mutexes, put them all together. You can actually, there is a library that does garbage collection. So way back in the prehistory of Rust, it did actually have garbage collection built into the early versions of the language, and they just decided to rip it out because they wanted to target more of this like system programming niche. But if you want to go back to having garbage collection, you can, but you have to have a library that isn't part of the core language. Yeah, they do their best to kind of, have different ways of dealing with things. Like self-referential structs are another thing that like you can't express in Rust without some sort of help. So they created a special type for it. And kind of exciting and not exciting thing about this is that it's all sort of, it happened in the not that distant past. So, maybe what you need isn't there yet. Maybe you run into some problems or it's not all that well understood yet. Well, maybe it is. It's sort of the lay of the land when you're working with something that's sort of new and exciting. And yeah, just hitting unsafe. If you want to just jettison all of the rules, unsafe will let you do. Essentially get around any rule that Rust will have for you. You can get around it by dereferencing pointers. You can include raw assembly if you want, or in CPU intrinsics. You can build an operating system in Rust if you want. There's this whole Rustonomicon, which I think is a fantastic name for the book of unsafe Rust, the dark arts of unsafe Rust. A little bit of a sense of humor is fun sometimes. Just had there's all this stuff that I want to talk about, but there's only so much time in the day. But the kind of last major thing I wanted to mention was Cargo, right? Cargo is a sort of package manager for Rust. It's how your libraries are structured. It's how dependencies are managed, that sort of thing. So the Cargo, there's this root configuration file, which is just a TOML file where you can specify, the things about your package. You use Cargo to specify all your dependencies, like what version of it, what features you're using, if you have dependencies that are just used for development, not for actually building it, like a dependency that's just in your tests, for example, you can specify that there. Or if you want to build without the standard library, you can do that too. If you want to target a microcontroller and you can't use a standard library, there won't be an operating system, and so you can't depend on having the standard library. You can specify that in Cargo and some of the other places with keywords. Anyway, that gets a little complicated. There's this whole features system, which is kind of like a formalized series of if-defs. This is the equivalent of if-defs in C and C++, where you have these features specified in the cargo.toml file. And then the features are also the dependency graph interacts with these features. So your dependencies might pull in a feature, or you can use the features to tell your dependencies what other dependencies to pull in. So you might use a crate that, like under normal circumstances, like integrates with the standard library, like for random number generation or something. But maybe you want to use it in a place where you're not going to have the standard library. So you can kind of use these features to control like how your dependencies build themselves, which can be kind of fun and useful. This is just a little example of how it shows up inside Rust code. And then tests. We talked about this earlier too, that that cargo runs all your tests for you and does the documentation. So it generates this kind of nice, just like the tools for C and C++, or like Java doc, other languages. Obviously Rust has that too, and that stuff is in cargo. Builds your dependencies, runs your tests. This is something that's kind of cool. So in the documentation for Rust, you write the documentation, the doc codes in Markdown. And you can stick code inside of Markdown with those little 3 tick braces, and then you write your code and then you close with the 3 tick braces. And so it's great for like putting code examples in your documentation. Well, Cargo does this thing where it will compile and run all of your tests in documentation. And so if your documentation is wrong, like the examples that you give in the documentation don't compile or they panic, that will show up in the Cargo test. When the tests get run, Cargo will run tests out of your documentation, which is pretty cool. There's like a benchmark harness that's built into it too. And then there's like plugins. So there's this tree plugin that does this nice little graph of all your dependencies and your dependencies. So you can figure out what's in your binary and why. Rust generally will generate a static binary for most applications, but there are like different modes where you can generate like a C dynamic library or a precompiled Rust library, that sort of thing. Or there's this cargo subcommand that tells you what you're using that there are new versions of, which is kind of cool. There's this ASM keyword that is this really kind of neat interface for just getting actual assembly code out of your functions. So, cargo ASM will let you see disassemble your functions after they've been compiled and then disassembled. And then this is just kind of one that's really fun. It's Clippy. So you remember Clippy from Microsoft Office from 20 years ago, where Clippy would be like, it looks like you're trying to write a letter. Would you like some help with that? And so Clippy is like the linter for Rust that's like really pedantic. Like there's a shortcut for this. Are you sure you don't want to use it? So it will kind of, spot all those things for you and like suggest like, maybe you want to do it the Rust, the more idiomatic way or whatever. It has an automatic formatter so that you can, fight with your coworkers over exactly how much white space you should use, how many spaces or tabs and what line you can specify all of that, and have it automatically format all your stuff. And then there are some things in Rust that are like, it is still a little bit new, right? Not everything is done yet. So an example of that is like these constant functions. So C++ has this. This is like, and it can be really useful to have generics like values inside of your type system for doing things like specifying the size of an array. So that way you can allocate it on the stack. It can all be like specified in a generic. So you only have to, write that once. And that sort of code is, it doesn't exist yet it's only in the beta and unsafe kind of nightly compiles. And actually I tried to use it. I thought like, maybe I'll get away with using this beta feature, but this beta feature causes the compiler to crash. So they sort of, if you want to be on that bleeding edge, they'll let you be on that bleeding edge. You just have to like opt into it with a whole bunch of keywords like, yes, I want to run the nightly compiler. Yes, I want to turn on this experimental feature. Yes, I know that the rug's going to get pulled out from under me at any time, that sort of thing. But yeah, there's a lot kind of, they're still working on the language basically. for specialization. There's a whole book about unstable Rust. Yeah, Rust uses LLVM, that little dragon. I spent entirely way too much time making that cute little graphic. I mean, and by too much time, I mean 5 minutes or whatever that it took to find the images. But anyway, yeah, Rust is riding on the back of LLVM's dragon, which does a lot of the hard work. It does actually the code generation into the actual machine language, right? LLVM is a really cool project.
Kendall, you mentioned the feature of cargo that will take the documentation and actually compile Rust code snippets that are in it.
Yeah.
It sounds like a stolen from the Python, what is it called?
PyTest.
Jupyter Notebook.
Oh, Jupyter too, yeah.
Oh, yeah.
Jupyter Notebook is like a lot of descriptive words and stuff with some snippets of code that actually run.
Yeah, I love Jupyter Notebook. I use that for a lot of my when I did my PhD. I use that sometimes for my for the stats. Well, I got started with R first, and then I realized how much I really hated the R as a language. R is really kind of complicated and difficult to deal with, but yeah, Python was really nice that way, and Jupyter Notebook's really nice.
Weird, but nice.
Yeah. And the fact that it's like data scientists and other people who aren't computer programmers, they're not primarily software developers, but they can still write and understand Python, at least for data science and statistical analysis stuff and doing data visualizations and stuff like that. I think when I did the little analysis of the RockDev job survey stuff, salary analyzing state, compensation survey. I used, that stuff because it was fun.
Speaking of, we got to get on that.
Oh, do that again for the next year?
Yeah, it's usually September, so
yeah,
we got a little time.
Well, there'll definitely be more people doing remote this year, probably. That seems highly likely.
Yeah, the questions might have to change.
Income might go down for all of the folks that are laid off and furloughed.
Yeah, that's true. So I have a handful of slides left. Let's see. I'm mostly through, but I kind of a bunch of caveats, right? So Rust is kind of exciting, and it's exciting because it's new and it's used in this sort of exciting areas like operating system kernels and databases and kind of bare metal programming. But there's a lot of caveats that go into not everybody does that sort of stuff, and so it's not always appropriate to use everywhere. There are a lot of existing systems. If you're actually going to use it in a production thing, you got to figure how many people know it, how much does it cost to hire them, can you hire consultants, is it going to be around 10 years from now, is it going to continue to be supported? There's all these other complicated factors that go into a language other than just is a language neat and is it kind of fun and interesting and something new, right? So Rust has a lot of a lot of people are excited about it, and so there's also a lot of enthusiasm that's also maybe sometimes a little bit over the top enthusiasm, everything should be written in Rust, and that's not real world. It's not the real world. And it's important to keep that in mind sometimes. There are some things in Rust is still new, so they have this whole series of are we X yet? So can you use Rust to build a GUI? And no, the libraries, the GUI libraries, there are definitely there's multiple people who are attempting it, and some of the libraries might be usable, but it's they're all very new. They might have bugs. There's not it's not like Microsoft where you have a huge standard toolkit that's been used by tons of people yet, right? It's still really new. And the same thing is true with for game development engines. I think someone was mentioning that they had a friend who was developing a game engine in Rust. Yeah, this sort of this cool stuff that you can do. It's it's an exciting technology to use for stuff like that. But it's also it's not like the big projects that have been around for a really long time. I mean, like Unreal Engine isn't written in Rust. So, there's a certain amount of like trade-offs you have like with dealing with a new language and all the stuff that goes along with that. But like, nevertheless, some people are actually like rewriting stuff. And I mean, if it's the right situation, the value proposition of Rust is really kind of cool. So I just have two articles here. One is by Dropbox, who rewrote the heart of their sync engine. They rewrote it in Rust. And, again, like, this article, they wrote up this, pretty long article about their experience rewriting their sync engine in Rust. And they're actually pretty realistic about it. Like, rewriting your software is usually a terrible idea. You have to throw out a lot of old code. There's a lot of like experience and bug fixes that went into that old code. And a lot of like, there might be a lot of tech debt, but there's also a lot of knowledge in some of that legacy code, and might be throwing some of that away. But, if it's the right kind of perfect use case and you might be having problems anyway, maybe it's worth it. And so, Dropbox, they did it. They rewrote their sync engine. They think it was worth it for them at least, but, who knows? It's always a very complicated decision whether you want to take some existing system and rewrite it. Another example of that, though, is like Discord moved from Go to Rust for one of their services. And they did it just because they wanted to get rid of the latency spikes from garbage collection that's inherent in Go. So they, just had the write-up on, why they chose it, why they changed it, their sort of experience with it. They were happy overall with what they did, and they kind of gave their, like, this is what we got out of it. We got about the same CPU performance, on average anyway. But what we don't have is those big latency spikes. So, they had more consistent performance and, more, higher quality of service. And that was important for them and their application. So, in that case, it worked out for them. That was another success story. There are some frameworks for doing like web services and websites. And I mean, this is kind of an area where it's like, it's interesting and it's cool because, it's something new and different, and it's, it's fun to, it's an opportunity to learn Rust and actually do something with it. But I'm not sure that Rust, that web is the right framework, right? Because, maybe, performance isn't as important as how cheap it was to write the code in the first place. And there are, so many existing libraries and tooling for websites that, maybe not the best, thing to start a new project in or to do a web project in, but it's there. And there are people that are interested enough and care enough to make the sort of, those sort of frameworks and start working on them. And then there's another set of people who are like interested in like deploying it for like embedded devices and Internet of Things devices. And Brian Cantrell would like to have all firmware be written in Rust. It's another kind of potential application for it. Anyway, and the last thing I had was just this sort of like, and I think I'll skip it because we're already over 2 hours, but this sort of like troll, slightly troll a video about, should we rewrite the operating system in Rust, right?
Kind of like that ship has sailed. There's already one. A Linux-like operating system written entirely in Rust.
Yeah, there is what's it called? React OS? No.
Okay. I forget what it's called.
React Native?
No, that's a web technology. Rust, I mean, Redux is the name of it. Yeah.
Yeah, Redux.
So that's like the big project. And there's a handful of projects. So I kind of enjoy that talk by that I started playing a little bit by Brian Cantrell. Of course, I like a lot of Brian Cantrell talks. But yeah, there's like a handful of programs or like operating system projects that people are just doing for fun. There's someone named Philip Opperman who's just writing a like it's called Philip Opperman's blog operating system, and he just has like a whole series of blogs about like how to build an operating system in Rust, which is kind of fun and interesting to read and follow along with. Obviously not something that we're going to be actively actually running for any sort of production use, but it's a kind of a fun and curious thing to look at. It's an interesting artifact.
The person that you mentioned that said that Rust should be used for all bare metal stuff or for all embedded stuff. If you think about,
there are people that are thinking about that.
If you think about one of the most significant applications in that context, where you're talking about autonomous cars, think about taking input from LiDAR, radar, cameras, all over the freaking car, and making decisions in time not to hit something that's in front of you.
Yeah.
You'd like to be fast and you'd like the code to be safe.
Mm-hmm.
So there's a pretty good application for Rust, but the libraries aren't quite there yet.
Yeah, I think that's a real, I think I agree with that assessment. It's like, it's really interesting and the value proposition is there. And they're probably a little scary because like they started these projects a long time ago. Like when the autonomous car projects were started, like Rust wasn't near stable enough to be considered to be used in an application like this. And now they've built the systems in whatever they built them in. And whether whether Rust actually ever gets used for that is kind of questionable. But yeah, it does seem like a really good application for it, right? Because you don't want like your code crash to become a literal crash.
C++ is typically what's being used, and a specific version of C++ is an automotive standard. And there's a whole bunch of hooks that one has to conform to in order to get certified as MISRA standard, M-I-S-R.
Oh, wow.
And Rust makes most of those things that the MISRA checks look for not possible in the first place.
Okay.
That's irrelevant.
That's kind of cool. I did not know that there was like a special, C++ and certification for automotive use.
Oh, yeah.
Cool. Well, that was really all I had in terms of slides. So, I guess we can discuss and talk about a little bit if you'd like. Or, when we're done with that, I guess, we've kept you for like a little over 2 hours now. So eventually people will want to, get on with their evenings, I suppose. But